Hello, if you're watching this video and you haven't yet tried this worksheet, please do pause the video, download the worksheet, and give it a try. So I'm going to just talk you through the recitation worksheet for this week. And the first few problems, what you're supposed to do is you're supposed to just graph the parametric curves. This is something you probably did in pre-calculus or maybe Calc 2, I don't know. But it's a pretty straightforward process here. We have a range of values for t, and we're going to plug those values in here. And so essentially the way that this is going to work is that x is equal to t minus 2 and y is equal to 3 minus 2t. I didn't label this, but hopefully you can figure out where those labels are. I also didn't give myself much room, but I can do it up here. So I have values for t, and I have values for x, which is t minus 2, and y, which is 3 minus 2t. And my values of t are going to start at -2. I don't know that I need to plug in all of these, especially since this is just going to be a line. But let's go ahead and plug in a few of these. For t equals -2, you get x equals -4, and y is equal to 7. Yeah, 3 minus 2 times -2 is 7. When I plug -1 into this function, I get -3 for x. Maybe I'll just do the x values first. Probably be more efficient. And then this will be 3. So there's my x values for these particular values of t. Once again, nothing magical about those other than they're in the range of values that I'm interested in. And then let's do the same thing. Plug -1 into this, and we get 5, 3. This will be -1. And then this is -7. So now I just go ahead and plot these points. So when t equals -2, I get -4 and 7. Let's see, -1, -2, -4, 5, 6, 7. So that's right here. There's t equals -2. When t equals -1, I have -3 and 5. T equals 0 is -2 and 3. I think you can probably see where this is going. When t equals 2, I've got x equals 0, y equals -1. And when t equals 5, x equals 3, y equals -7. Just down here. All that's left is connect these with a beautiful line. Yeah, good enough. And so that's it. I mean, if you want to label it, that's fine, but you don't have to. Okay, let's go down here. Things get more interesting when you have these sines and cosines, but since we're dealing with values between 0 and 2 pi, let's just pick our favorite angles. For example, start at 0, t equals 0. You get 3 times the cosine of 0 for x. Move this thing over. Okay, so here's what I'll do. Pi over 3, pi over 2. Yeah, I'm going to get sick of doing this, and you probably are already. But anyway, 3 times the cosine of 0 is 3. 3 times the sine of 0 is 0. So that's this point here, 3, 0. Then pi over 3, we're going to get 3 times the cosine of pi over 3. The cosine of pi over 3 is 1/2. So that's going to be 3/2. This will be 3 radical 3 over 2. Because the sine of pi over 3 is radical 3 over 2. Okay, so let's see if I got this right. 3/2. 3 radical 3 over 2. It's somewhere up here, let's just say. Then pi over 2, the cosine of pi over 2 is 0. Sine of pi over 2 is 1. So 3 times 1 is 3. That's right here. Yeah, I think you can see what's going to happen, but let's go ahead and follow through. When I plug pi into this, I get -3 because the cosine of pi is -1. This is 0. This will be 0, -3, 3, 0. So without filling in all of the dots here, because there's going to be dots in between, I don't know, like this here and here. I don't know, if I were to fill in more of the values, I would get a nice circle. Wow. Oh, isn't that nice? So anyway, that's basically what that one is. Apparently those dots, not quite right. Okay, let's go up here and see what happens when we have this. So here, here again, we can make a little chart. Value for t, x, and y. And it looks like t goes from -4 to 4. All right, well, because there's a sign there, it's going to be a lot easier if I use values that I know for, yeah, this is just going to be ugly, I guess, no matter what. So maybe I'll start with -pi, -pi over 2, 0, pi over 2, pi. Might as well do 4, whatever. Okay, so this will be -pi over 2, which is, what, about 1.5, a little bit more. And then 3 times the sine of -pi. The sine of -pi is 0. Sorry, so that'll be 0. Then -pi over 2, we get pi over 4 for that, because I'm doing x is t over 2 and y is 3 sine of t. So now this one is going to be -3, sorry, because the sine of -pi over 2 is 3. Let's just fill these in here. And this will be 3 times the sine of 4, whatever that is. And then moving down this, I get this, pi over 4, pi over 2, and 2. Okay, so let's see if I can graph this. So starting at x equals -pi over 2. So let's see, -1, -2. This is a 0, 1, 2. Okay, so -pi over 2 and 0, so that's going to be right about here. That's t equals -pi. And of course, -4 is going to be a little bit to the left of, oh, actually, it'll be at -2. We'll fill that in a sec. Then the -pi over 4, this is when t equals -pi over 2. I have -pi over 4. Which is like 7.7 something, and -3. So you're down here somewhere. Then we're at this point. Then we're up here somewhere. I'm kind of fudging it a little bit. And then I don't know exactly what the sign. I'm just going to put this down here. We'll just stick a dot right there. So here's t equals -4. This one is t equals 4. But you can see what's happening here. You end up with this, woo, nice sine curve. There it is. One more of these, and then we'll put it all together. Okay, so this is almost exactly the same situation, only we've switched the x and the y. So let's do this. X is 3 cosine of t. Y is t over 2. So let's do -4, -pi, -pi over 2. There we go. Oh, this has a different range. I didn't even notice that. Okay, so we're going from -2 pi to 2 pi. All right, I'll try to blow through this pretty quickly. 3 times the cosine of -2 pi is 3. And this will just be -pi. That will be -3. times cosine of negative pi is negative 3. And then this will be negative pi over 2, pi over 4. This will be 0, 3, 0, 0, pi over 4. I'm just plugging in these values for t into the 2. 3, negative 3, and 3, and then this will be pi over 2 pi. Okay, let's see if I can fill this in pretty quickly. Okay, so we start with x equals 3 and y is equal to negative pi. So 3 is right here, and negative pi is going to be a little bit below. So that's t equals negative 2 pi. Then we have negative 3 and negative pi over 2. So that's right, negative 3. So we're back here somewhere. And then negative pi over 4 and 0. And then here, I'll just do my best. Because I know what this is going to look like eventually. So there it is. So there's that 3 pi. It's right there. So anyway, this thing is just another, looks like another sine curve. There, the best I can do. And if you want to, you can throw a little, throw a little arrow on there to say that's the direction we're moving. Suppose I could have done the same thing back here, going that way. Okay, so this is all in service of reminding you how parametric curves work, because these vector functions, vector valued functions, or space curves, they're sometimes called, are just three-dimensional versions of these vector value or parametric curves. So let's maybe talk about these things without necessarily computing the values like we did up here, but more just thinking about what these will look like. So with number 5 here, this thing is going to have, let's see, you have the cosine times j and sine times k. So anytime you see sine and cosine, what you should think of is you should think of a circle, like this circle right here. This one has a cosine and a sine. So the same thing goes here. This is going to have a circular element to it. But it's not just any circle. This circle is going to be a circular in the YZ plane. Notice that the J and the K, that's Y and Z. So this will be a circle in the YZ plane. Now what's going on here is that while this thing is circling around in the YZ plane, the x value is constantly moving forward, if you will. So remember that in all these graphs, the x is pointing out towards us. The y and the z are kind of in the plane of the page. And so the one this is going to match is letter B, because notice that this one is the one, see if I can do this right this time, that you're going around in a circle in the YZ. So here's y is this way, z is this way, and so circles would be sort of moving around this way, but then you're moving along the x-axis, so that as you're going around in circles, you're kind of coming out of the screen. It's coming out towards you. This is a helix. But anyway, so that one is letter B. So let's fill in that little bubble. And in fact, the next two, I think, no. Where are they? Well, the next one for sure is going to be, I'm going to mark that off. It's going to be similar. Notice that there the circular motion is in the XZ. So XZ plane has a circle. Okay, so this thing will be XZ, and so the Y, this Y variable, that's moving just along. And so here, the circular motion, it's going to be that one. But this circular motion is happening in the x, z planes. And so that gives you this clue. And then the y variable just continually, you're moving this direction. Sort of this circle is kind of unspooling in that way. So that's going to be letter C. Let me go hunt up there's one more like this, I believe. It's number 9. Notice number 9, it's basically a similar situation, but now it's the x, y has circles. Circles, good enough. So that one, the x, y has the circle, so here's x, here's y. So you should expect circles like this, but you're moving upward as you're doing that circular motion. And so, as you've probably figured out, it is letter A. Okay, next one. Let's just plow through the rest of these. The next 3, so there's 7, 8, and 10. The main difference is this, what's happening in the z direction. So x and y, you have circles in all 3 of those. But let's talk about 7 first. 7, you have a circle in the xy direction. The z coordinate is always 1. And so this circle is just going around its letter F here. So that's going to be this one. Now, as far as distinguishing between number 8 and number, this one was A. Number 8 and number 10. Number 8, the circles are, you're stretching. So stretching as t increases. And this one, natural log of t, let me just show you what natural log of t looks like this. So you're actually kind of compressing this spring, if you want to think of it as a spring. E to the t, here's what e to the t looks like. And so the further you go as t gets bigger, the z coordinate gets further and further away at an exponential rate. So the one that is doing that is letter D. You see that one? As you go up this spring, it's getting stretched and at a greater and greater rate. So that's letter D here. And then the last one, process of elimination, must be letter E, but we can talk about it nonetheless. Here, as you go up the spring, it's getting more and more compressed. Sort of the rings of the spring are getting closer together. So there's that. All right, a little bit of calculus. Limits work the same in vector function as they do in regular calculus, so this shouldn't be too bad. Basically, you can just do these limits one at a time. So we can do the limit as t approaches 2 of sine of t minus 2 over t minus 2. Hopefully you know how that works. That's just going to be 1. The limit as t approaches 2 of t squared minus 5t plus 6 over t squared minus 4 is the same as the limit as t approaches 2 of t minus 2, t minus 3, t plus 2. We're going to cancel those, and then we can just plug this in. And we got negative 1/4, and then the limit, the final limit, and then we'll put it all together. Let's see, 1 over t minus 1/2 all over radical t minus radical 2. You have a couple of options here. We could do some algebra, but we could have done L'Hopital back on the second one. Let's do L'Hopital just for fun, since when you plug in 2, you get 0 over 0, so we can just do derivatives here. So here, L'Hopital. Put a little hat on that O. And you get this is going to be the same as this. Let's see, 1 over t. The derivative of 1 over t is negative 1 over t squared. Derivative of 1/2 is 0. Derivative of radical t is 1 over 2 radical t, and that's also 0. Let me clean this up a bit. The whole point of doing L'Hopital is that now you should be able to clean things up to the point that you can just plug in the number. I suppose I could just plug it in right now, couldn't I? Yeah, I don't see why not. Well, let me clean it up nonetheless. So I have 2 radical t. 2 radical t over t squared. There's a negative in there somewhere. Now I can just plug in my number here, and I get negative radical 2 over 2. Oh, don't box it up yet. And so that means, so we're going to take all of those and construct the, so this will be 1i plus, minus 1/4 j minus radical 2 over 2k. And that's it. That's your limit. All right, final thing. So find the point on the curve that is closest to this point. Okay, so once again, we've got this situation where you have x is 3 cosine of t, y is 2 sine of t, and z is sine of t. You know the distance formula. It's going to be the square root of x minus 0 squared. I'm doing the distance between x, y, z, and the point that's given there. Let's see, and then y minus 1 squared, z minus 2 squared. Now I'm going to take these things and shove them in there. Oh, and I'm also going to rewrite this. So this is going to be the function f. Is going to be the distance squared. And it's a trick you probably did in calculus at some point when you're doing optimization. It's just a pain to deal with that radical when you're doing distance, so we just get rid of the radical by squaring everything. It all works out. But anyway, so this will be 3 cosine t squared. That's the x value. And then the y value is 2 sine t minus 1. Square that thing, and then sine of t minus 2. All right, well, you know the drill here. We're going to do a derivative. And I could square everything first, but we all know the chain rule. And so let's just use the chain rule here. So we have f prime is going to be 2 times 3 cosine of t times 3 sine of t. Whoops. I just realized I need a negative somewhere. Let's put it out front. And then plus 2 times 2 sine of t times 2 cosine of t. The derivative of 2 sine of t is 2 cosine of t. And then 2 times sine of t minus 2. This is to the first power. If it bothers you, I'll put it in there. Times the cosine of t. All right, let me clean this up. You know the drill. We're going to take the derivative, set it equal to 0, solve, and then hope that what we get is a minimum. It says closest. Okay, so this, let me just clean this up a bit. I didn't do this ahead of time. 18 sine cosine. That's the first bit. Ugh. Okay, this is going to be plus 8 sine cosine minus 4 cosine. That's the second bit. And then plus 2 sine cosine minus 4 cosine. I think I got all that. Guess if it doesn't work out, then yeah, I'll know that I made a mistake. But anyway, so there it is, and then we set this equal to 0. Let me clean this up a little bit more. This will be negative 10 sine cosine. Oh, I missed the 2 there, so negative 8. Negative 8, yeah, negative 8 sine cosine minus 8 cosine. All right, well, this looks promising. I certainly can factor this. Negative 8 cosine of t times sine of t plus 1. Okay, so what this gives me is it gives me the following. Either the cosine of t is equal to 0 or sine of t plus 1 equals 0. So this, we all know that gives you these pi over 2 and 3 pi over 2 are the different solutions there. And here the sine of t is negative 1, and that happens when t is 3 pi over 2. So I guess there's really just 2 solutions. I guess we're assuming t can only be between 0 and 2 pi, but this thing will cycle around, so these are only 2 things that we have to worry about. So how do we know which one is the max and which is the min? Well, I'm going to use a second derivative test. You can use the first derivative test if you prefer, but I like second derivative. Second derivative test. Remember how this works. You're going to do the derivative of the first derivative. So I'm going to use this line here, mainly because that's a simplified version. I don't have to do as much messing around. Looks like I have a product rule that I'm going to have to deal with. So let's do that first. So this will be sine of t times sine, negative, and then cosine of t, I believe that's right. So using the product rule there. And then this one is just 8 sine. And then the way that we're going to do this is we will, here, let's clean this up a little bit more, I suppose. This will be negative 8 times cosine squared t plus 8 sine squared plus 8 sine. And so then we're just going to plug in our 2 candidates. F double prime of pi over 2 is going to be, let's see, pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this will be 16. And that is greater than 0, which means you're at a relative minimum. So pi over 2 is a relative minimum. And then we can do the same thing for 3 pi over 2. Let's see, the cosine of 3 pi over 2 is 0. The sine of 3 pi over 2 is negative 1. Oh, interesting. So this becomes 0, which is a don't know situation. So maybe we're stuck doing the first derivative test. Crud. Let's try and avoid it. Okay, we'll do the first derivative test for this. So first derivative. And what is the first derivative test? Well, you do the first derivative at some point to the left of 3 pi over 2, and the first derivative at some point on the right, and see, and we'll compare. So let's go back to the first derivative, which was, where was it? Oh, it's right there. So I'm going to use this here, just so you know, this here, that is the first derivative. Okay, so we're plugging in pi. When we plug pi into that, the cosine of pi is negative 1, so this becomes 8. You can do it. Go ahead and plug it in if you don't believe me. At 2 pi, cosine, that's going to be 1. It's going to be negative 8. Okay, so notice what this means is that this is increasing and then decreasing. And so 3 pi over 2 will be a relative max, because you're going up and then down. And so the relative min is here. I suppose that I'm cheating by not going through a little bit more work to figure out the, make sure that this is an absolute minimum, but we're just going to go with this. So here we're going to go up there, and we'll do t equals pi over 2, which means that x is equal to 3 times the cosine of pi over 2, which is 0. That's going to be 0. Y is equal to 2 times the sine of pi over 2, that's 1, times 1, which is 2. And z is just the sine of pi over 2, which is 1. So the point on the curve, so the answer, is the point x equals 0, y equals 2. There. That is the point that is closest to 0, 1, 2. All right, that's it. So I hope this is helpful, and do let me know if you want any additional instruction on this. All right, thanks so much.